All right, section 3.4, the chain rule. This is one of those sections that can be a little bit difficult. All right, so of all the different rules and processes that we're going to talk about how to find derivatives, this is probably the one process that gives the most difficulty. And it's simply because it's not just a single step by step process that I can give you that works for every function. It's a process that involves multiple steps in differentiation, but the process changes depending upon the makeup of the function itself. All right, so I'm going to explain the process, how it works, or why we have to follow this process in differentiation. And then I'm just going to give you several different examples of different types of functions and combinations of functions and what to look for to properly apply the chain rule when you're finding the derivative of a function. Now, the reason for the chain rule right, comes about because of composition of functions. Right? So we've mentioned composition of functions before. So I'm looking at f composed with g of x or f of g of x, right, that notation. Before I begin with the chain rule itself, just kind of again recognition or recognizing, in our case, not taking functions and composing them to form a new function, but recognizing that our function is the composition of two functions or more, because we'll also see situations where maybe there's a composition of 3 or even 4 functions. There's no limit to this. All right, so it's recognizing, so say for example something like this, f of x equals the square root of x cubed plus 4. Right, a square root function, obviously. But I'm looking at this function as the composition of functions f and g. Remember when you're dealing with composition of functions, you always kind of think of an inner function and an outer function. All right, so what is the outermost function, and then what function is inside of that function? So in other words, if I look at that square root as an outer function, and then the radicand x cubed plus 4x as our inner function, and I called the outer function f, I called the inner function g, that's purely arbitrary. But then if I look at the function f composed with g, which is f of g of x, right? Remember where you plug g into f, then I'm plugging x cubed plus 4x in place of x in our square root of x. And I get that function cap f that we have above, x cubed plus 4x. All right, so that's what's going to be involved with, first of all, recognizing that you have the composition of functions, because then when you get to the differentiation of that function, it then means that not only do you have to differentiate the outermost function, but you also have to differentiate the inner function, and however many functions you have wrapped within your main function. So you can kind of think of this like as a peeling back layers of an onion kind of thing. You peel off the first layer, that's your outer function, and if there's another layer in under there, then you then have to differentiate that. You have to peel that layer off, and if there's another layer under there, you have to peel that one off, and so on until you peel back all the layers. But you always think of this as working from the outside in when you're finding the derivative of a composite function. You differentiate the outermost function, then you differentiate the function that's inside of it. If there's a function inside of that, you differentiate, etc., etc. Now, there's some different notations, and as always, like we said, we've got to be very clear on the language, the terminology, the notation, because if you don't understand the terminology, and if you don't understand the notation, then it's going to make it very difficult to understand this concept. And this is especially true with the chain rule because there's so many moving parts to this. So for the chain rule, here's our definition. For if I have two functions f and g that are both differentiable, and we're going to form a new function cap f that is the composition of f and g. So this cap f is f of g of x, where we take g and plug it into little f, we'll call it. So then our function cap f is the composition of those two. So then the derivative of the main function, cap f prime, notice then, is the derivative of that outer function f with respect to its inner function times the derivative of the inner function. So notice in this case that g of x didn't change, right? So in other words, I differentiate f as a function. F is a function of g of x. G is a function of x. So you can think of it that way. So I differentiate the outer function f with respect to its inner function. So I get f prime of g of x. And then I go inside of f and I have that function g, which I then differentiate g to get g prime. Here's another notation. I have a few different notations. Hopefully one of these will help to make it clear. So let's say that I have a function y defined as a function of u. So y equals f of u. And then that function u itself is a function of x. So u is g of x, u is a function of x. And this is where all that language catches up with you if you haven't been paying particular attention to the language and the way that we describe all this stuff, right? So when we say f of x, what do we mean? We mean f is a function of x, right? X is our input into the function f. When I say y equals f of u, that means y is a function of u. U is the input into that function f. And then we're defining u as g of x, where u is the function g that is a function of x, which is the input into u. So x is plugged into u is then plugged into our y. So then when we differentiate that function, we work from the outside in. So we say that y prime is the derivative of the outer function, which is f, so it's f prime of u with respect to its input, times the derivative of that inner function, which would then be u prime. Here's another notation. This is the dy dx notation. Think of it this way. If I'm differentiating y with respect to x, so with respect to the notation I have above, since y is a function of u, then I would first differentiate y with respect to u. That's dy du. Then I would have to differentiate u with respect to x, du dx. And notice, I've told you before with this notation, it works algebraically. If you take dy du times du dx, right, the du's divide out and you're left with dy dx. So those are equivalent notations. But again, you have to think in terms of an inner function and outer function. What is my outermost function? What function is inside of that? And then do I have another function inside of that, etc. Now, that is also in conjunction with all the other processes that we've talked about, like product rule, quotient rule, and so forth. So everything is in play, and that's what makes this really difficult, because you really have to be observant. You have to break that function down so that we make sure that we have differentiated every piece or every layer of the onion. So, for example, here's our power rule. Right, the power rule with those basic power functions. So power rule combined with chain rule. Here's what it looks like. If we have n representing any real number, right, that's with our definition. So if I have this function u equals g of x. Of course, if it is differentiable, we see that in all these definitions. Otherwise, I can't differentiate it. So if u equals g of x is differentiable, then the derivative of u to the nth power, right? So I take that function and raise it to the nth power. We still apply our basic power rule. We multiply by the exponent and then decrease by 1. Notice the base doesn't change, though. The base is still just u, whatever that u is. Then I multiply that times the derivative of the base with respect to x, because u is a function of x. Or in other words, if we differentiate this function g of x to the nth power, then again I apply the power rule just as we normally do. Multiply by the exponent, decrease the exponent by 1, but notice again I'm leaving the base alone. It's n times g of x, whatever that is, that's the base, raised to the n minus 1 power, and then I differentiate the base. That's my inner function. And so, I guess that the trickiest part with it is, like I said, with different types of functions that we're going to work with, you have to recognize what is the outer function, what is the inner function. And I'm going to give you some tips here as far as where to look. Now, once you have that figured out, I mean, then you're back to using your basic differentiation processes. So you're differentiating based upon the type of function you have. You're differentiating, like I said, using maybe a product rule, or if something like that is applicable. Okay, so the chain rule in itself is not anything new in terms of a differentiation process, other than it's requiring to differentiate multiple functions or multiple steps in the differentiation process. So here's a list of the different types of functions that we work with. Now, some of these we talked about how to differentiate already, some we haven't. So as we continue to add to that list of the types of functions that we know how to differentiate, we can also throw in the chain rule as part of the process. So for a power function, like we just talked about, if you have a power function, how do I recognize a power function? Well, I have some function raised to a power. All right. So I find the variable in the base, and then the exponent is some real number. So I'm taking this function g of x defined as the function f of x raised to the nth power. So recognizing the inner and outer function. The inner function is the base when you're looking at a power function. And then, of course, the outer function is the power function itself. So that's what I'm interested in right here, is recognizing what's the outer function, what's the inner function, and then we'll talk about the differentiation processes. For an exponential function, remember an exponential function is a function, say g of x equal a raised to some power, where in this case the variable is in the exponent. Right? The exponent is where you find the function, and the base is a constant. So in this case, the inner function is the exponent, and then the outer function is the exponential function itself. Okay? So in other words, when I differentiate an exponential function, I start with the exponential function itself, because you always start on the outside and you work your way in. I differentiate that function a to the whatever, and then I would multiply that times the derivative of the exponent, which is the inner function. Right? Now, we've talked about exponential functions a little bit. We're going to talk about them here again in this section, right, in terms of how do I differentiate an exponential function. Here's our trig functions. If I have a function g of x that is a trig function, the trig function is your outer function, your inner function is your argument, right? Because I could have a function in my argument, sine of not just x, but maybe sine of x squared, right? Where my argument is something other than just x, or is actually a function of x. So for a trig function, you look at the argument for an inner function, and then the trig function, of course, is the outer function, right? But that's the recognition. I'm looking at the argument for an inner function, and then the outer function is our trig function. Similarly, for inverse trig functions, we are going to talk about those upcoming section. And so we haven't talked about inverse trig functions yet, but it's basically the same idea as the trig function. If I have an inverse trig function, then again, I'm looking at the argument as my inner function. And then the outer function is the inverse trig function. Okay. So then I would differentiate, in this case, the inverse cosine function, however that works, we'll talk about that. And then I would have to multiply that times the derivative of that inner function, which is the argument, whatever the argument happens to be. Right? And then again, too, when you get to the inner function, it just depends on what f of x is. F of x may be a trig function itself, or f of x may be a power function, or f of x may be an exponential function. It just depends on what type of function it is. We then differentiate it. We've talked about log functions. We haven't talked about their derivatives yet, so we'll get into that again in an upcoming section in this chapter. So if I have a function defined as a log function, again, you're looking at the argument as your inner function. So it's kind of visually, I'm giving you the idea as far as what you're looking for to recognize the inner function and the outer function. So that once we start working with the process, and if you can recognize that, then the process just kind of moves pretty straightforward. And you start with the outermost function, work your way in. So for a log function, just like the trig functions, you look at the argument as your inner function. There's your f of x in this case. And then the log function, of course, would be the outer function. We still have to talk about how to differentiate those guys, but we'll get to that in this chapter. Okay, so those are pretty much the types of functions that we work with. And like I said, some of we've already talked about how to differentiate, some we haven't yet, so we'll have to get into those over the course of these next couple of sections. All right, so let's start with some examples. And again, I have to think about 10 examples that we're going to look at, just different combinations of functions and different things to look for. So starting with number 1. All right, and so there again is a basic power function, right? Y equals x squared plus 2x squared. So I've got a base that is a function raised to a constant power, right? So our outer function again in this case is the exponent, it's the power function. The inner function is your base. And so if I recognize that my function is a power function, how do I differentiate it? I differentiate using the power rule times the derivative of the base. So here's our power rule, y prime. 2 times x squared plus 2x to the first power, right? What's the power rule? We multiply by 1, multiply by the exponent, and then decrease the exponent by 1. Notice the base does not change. I then differentiate the base, okay? And this is probably the main mistake I see made with chain rule. It's doing too many derivatives at once. In other words, it's using the chain rule, the power rule that we used here, and at the same time differentiating the base. No, they're not done at the same time. They're done in a step-by-step process. So I differentiate on the outside first. I don't care what this base is. I don't care what that is. Ignore it. I use the power rule. 2 times the base, and then I decrease the exponent by 1. Then I worry about the base. And I look at the base and say, okay, that's just another power function. So now I differentiate x squared plus 2x like we normally would. So I've got 2 times x squared plus 2x times that derivative of x squared plus 2x, which is 2x plus 2. And there's our final derivatives. Okay. But that's the two main errors I see made with chain rule. First of all, it's trying to do too many derivatives at once. Secondly, it's not doing or going all the way to the innermost part of the function. Right, so like I said, peeling back the layers of the onion, we don't peel back all the layers. So those are usually the two main issues with applying the chain rule. So number 2, I've got the square root of x cubed plus 4x. Well, that's going to follow a similar process to what we've done before with power functions, because like we said, with radicals, we always end up writing those as exponents or in exponential form so that we can apply the power rule. Right, so again, once I write that as x cubed plus 4x to the 1/2 power, now again, I'm recognizing it, use of our power rule and the chain rule. So our outer function again is the power function, the inner function is the base. And so we apply our power rule, we multiply by 1/2, decrease the exponent by 1, that should be y prime. Okay, this is our derivative. But notice again, the base didn't change. The base is still x cubed plus 4x. So it's 1/2 times the base raised to the negative 1/2 when I decrease by 1 times the derivative of the base. Yeah, so I went ahead and rewrote first without the negative exponent. I went ahead and rewrote that as 1/2 times x cubed plus 4x. And I'm leaving off exponents here. That would be to the 1/2 power. There. So I went ahead and rewrote that with a positive exponent times the derivative of x cubed plus 4x, which is 3x squared plus 4. And again, that's just a basic power function. Right? So I use power rule again. And then again, I need my 1/2 down here. Okay? And then, of course, if you chose, you could rewrite that denominator as 2 times the square root of x cubed plus 4x. We've talked about before, and this is going to continue to be more and more of an issue because we're now dealing with functions that are much more complex, there's more parts to them. Once you do find the actual derivative, right, which we've done here, I'm done with all the differentiation, then it becomes the question of how do you want to rewrite the function, right? So we keep saying, you want to clean it up, try to make it look as presentable as possible without making that the big issue, okay? So again, perfectly fine there. If you want to rewrite that in radical form, you could do that as well. But that's, again, just another basic power rule. Number 3. Again, I've got a radical, right? So I've got the cube root, but notice also in this case I threw in a trig function as well. But again, recognizing that the outermost function here is the radical. And so I'm rewriting that first in exponential form, 1 plus tan x to the 1/3 power, so that I can use the power rule with the outermost function here. It's a power function whose base happens to contain a trig function. I don't worry about that just yet. I worry about that in the next step. So the outer function being a power function, we apply the power rule, which says multiply by the exponent and decrease the exponent by 1. Subtract 1 from 1/3, I've got negative 2/3. And again, the base doesn't change. I just differentiate the outer function, leave the base alone, then I multiply by the derivative of the base, which is 1 plus tangent. And so then again, I just rewrote this with a positive exponent. So I've got the 1 over 3 times 1 plus tan x to the 2/3. So just rewriting, dropping that to the denominator. And then times the derivative of 1 plus tan x. Remember, the derivative of 1 is 0, right? Derivative of a constant is 0. Plus the derivative of tangent. The derivative of tangent we saw was secant squared. So that's 0 plus secant squared, or just secant squared. And then I just rewrote that again. I moved the secant squared over to the numerator. And then, like I said, if you want to put that in radical form, go for it. Not absolutely necessary that you do that. And as I said, a lot of times you don't see us bother using the radical form. Leaving it in exponential form is perfectly fine. Okay. But again, that was power rule, power function on the outside. I was that cube root, so the 1/3 power, I used the power rule, and then I multiplied by the derivative of the base, which would be 0 plus secant squared, or secant squared, and then I just rewrote. Number 4, here's an exponential function, right? So again, it's recognizing the type of function that you have as the outermost function. So that's e raised to a power. So I'm looking at the exponential function base e, whose inner function is the exponent, right? The main function, the outer function, is the exponential function raised to that power. And then I look at the exponent as your inner function. So then when we differentiate y prime, how do I differentiate our exponential function base e? We've said already that the derivative of e to the x is e to the x. So here the derivative of e to the whatever is still e to the whatever. That doesn't change. That's the outer function. But then, because of chain rule, I have to differentiate that exponent. Okay? So the derivative of e to the whatever is e to the whatever times the derivative of the whatever times the derivative of that exponent. Now, once you get to this part, now I have to differentiate x times sine of x. You just differentiate that depending upon what it is. And in this case, that would require product rule. Right? So, as I go through each of these examples and I write out each of these steps, and this is where I strongly recommend, especially when you have chain rule involved, writing it out step by step. I tell you, you could consolidate steps if you're comfortable doing that, but I find that that's where we run into a lot of problems with chain rule. We try to consolidate too many steps, and we end up doing too many things in one step instead of doing one step at a time. So differentiate the outer function times the derivative of the inner function. Then, okay, I'm done with this. I can just carry that along. That's part of my final derivative. We worry now about this part. And it's okay, well, what's the derivative of x sine x? And then I start to recognize, oh, hey, I need product rule there. So there's the e x to the raised to the x sine x, that we already had. And then here's our product rule for the derivative of x sine x, which is our first times the derivative of the second. Derivative of sine is cosine, plus the second times the derivative of the first. Derivative of x is 1. So that's our product rule. Now, I'm done with the derivatives. I don't see any more ddx's anywhere in there. I'm done differentiating. Now it's all about rewriting, or how we choose to rewrite this thing. So we at least try to clean it up a little bit. And I'm just going to rewrite this as e raised to the x sine x times x cosine x plus sine x. And that's fine. That would be a perfectly good final version of our derivative. But notice again, exponential function base e, it's the derivative of the function base e, which is the e to the whatever, times the derivative of the exponent. And then again, you do whatever has to be done to differentiate each step along the way. Number 5. Here I've got several things going on. So number 5 is the function f of x equals e raised to the negative 5x power times the cosine of 3x. So there's several things to recognize here. First of all, the outermost function, the main function f, is a combination of the exponential function base e and the cosine function. But it's a product, right? So I have to recognize first that the outer function, the main function f, is a product of two functions. So the first thing I'm going to have to do is follow the product rule. All right, this is why I keep saying there's no magic pill for these guys. Every function is unique, and you just have to follow step by step, starting in the outermost and then working your way in. And in some cases like this one, the outermost process is something like product rule or quotient rule or something along those lines. So first thing I'm doing is following the product rule, which says what? F prime of x would be the first function, e to the negative 5x, times the derivative of the second, plus the second function, cosine 3x, times the derivative of the first. That's product rule. Then we go in the product rule and say, okay, I have to differentiate cosine of 3x, and I have to differentiate e to the negative 5x. I differentiate where it says to differentiate. This is why, I keep harping so much on making sure you write things clearly. And you have to be neat, you have to be organized, you have to write clearly, you have to understand what you write. So now I go in and I differentiate each place where I say differentiate. I find ddx of cosine 3x. So e to the negative 5x, I just rewrote that. And then our differentiation of cosine 3x, now that's going to require a chain rule because I've got a trig function that has an inner function, an argument of 3x. So I start with the derivative of the outer function, which is the cosine. The derivative of cosine is negative sine of 3x. Right? So we don't change the argument. We differentiate the outer function, negative sine of 3x. Then we differentiate the argument. All right, that's chain rule. Plus, we've got the cosine of 3x, which we already had. Then we differentiate e to the negative 5x. Now again, I'm differentiating e to the negative 5x. That's our exponential function, base e, that we just said has a derivative of the function times the derivative of its exponent. So this is the derivative of e to the negative 5x. This is the derivative of our cosine 3x. Now I'm looking at parentheses here. E to the x first times the derivative of the second. I'm looking at where I should have a parentheses there. Okay. And then plus second times the derivative of the first. Too many parentheses going on. All right, so again, we still then have to go back in here and differentiate where we say differentiate. All right, so everything gets carried on. Probably don't even need these parentheses. I'm looking at that. Yeah, because that's our first, D second, so that's fine. I don't even need those parentheses. It's probably why I didn't put the second one, because I didn't need the first one. Oh, I see why I put it, because of that negative in front of the sign. That's why, because I didn't want to make that look like E minus. So I put the parentheses, but I do need the parentheses there, just so it doesn't look like you're subtracting, but you're multiplying. Okay. Add multiplication right there. All right, I see why I had that now. All right, so again, each step of the way we go in and differentiate where we say to differentiate. So everything else just carries along, right? So here's our e to the negative 5x. There's times our negative sine of 3x times our derivative of 3x, which is 3. And then the second end of it, or the back end of it, plus cosine of 3x we already had. E to the negative 5x we already had, times the derivative of negative 5x, which is negative 5. Right? So like I said, you've got to be organized, you've got to be neat, each step along the way. And then you just differentiate as you come across a ddx. Now, once I'm done with all the differentiation, that's it. All right, there's my derivative. The rest of it, again, is just cleaning it up, making it look a little bit nicer. So I rearranged these factors in the first part of this. There's the negative 3. There's the negative 3 times that e to the negative 5x times the sine of 3x. So there's this guy. So just rearranged. I brought the negative and the 3 up to the front. And then the back end of it, there is a negative 5 over here. So I went ahead and brought that to the front. So that would give me minus 5 e to the negative 5x cosine 3x. And I just rearranged those two just to make them kind of match the first part of it. Right? But the order of the functions, when you're multiplying a bunch of functions like that, the order of those functions is not critical. We just try to write them to where they kind of visually look most appealing, or at least complicated. Right? So I just kind of cleaned it up, made it look nice. But I definitely, the step above, if you left it like that, I'd take a point off for that. I'd say, look, clean that up. Bring those constants to the front. Right? Bring those negatives to the front. That kind of thing. Number 6. Ooh, that looks like a bunch of mess right there. This actually is not a difficult problem. It just looks that way because of what's involved. But let's look at the original function. So this is number 6. I've got the function h of t equals t to the 4th minus 1 cubed times t cubed plus 1 to the 4th. Now, here's option number 1 for differentiating this function. Those are nothing but binomials raised to powers. You could choose to take t to the 4th minus 1 and cube it. You could take t cubed plus 1 and raise it to the 4th power and multiply all that stuff out and then multiply them together, right? You end up with a big bunch of polynomials and stuff. You could do that. But what if that was t to the 4th minus 1 to the 10th power? Or t cubed plus 1 to the 12th power, right? I don't think I want to go that route. I mean, it's not difficult, but it's very time consuming, right? So fortunately, with the use of the chain rule, we can get around that. And we're actually even going to look at another way that we can do these in an upcoming section once we talk about the log functions and how we differentiate those guys. All right, so there's going to be another way that this can be done. All right, but here's what I'm looking at. So h of t, I'm looking at the main function itself, recognizing that is a product, right? It's the product of those two binomials. So first and foremost, I'm applying the product rule here. So h prime is our first, t to the 4th minus 1 cubed times the derivative of the second, plus the second times the derivative of the first. Right? That's product rule. That's all that is. Then I go in and I differentiate where I say differentiate. So I've got d dt. Now notice I'm using t. That's my variable. Try to be consistent with the variables. Now, recommendation too. I know people ask me this all the time. A lot of people don't like using t as a variable because it ends up looking like a plus sign and could be confusing. If you don't like the variable that's used, if they're using t and you would prefer to use x or something else, that's fine. Change the variable, rewrite the function with your new variable, go through your differentiation process. The only thing we would ask is that once you're finished, you bring back the original variable, right? Because this is not h of x, this is h of t. So if you want to rewrite that as h of x and write it that way and then do the differentiation, that's fine. I don't have a problem with that. Just make sure, though, you do bring back the original variable once you're done. Otherwise, that will be a deduction. All right, so then we go in, we're going to differentiate where we say differentiate. So there again, just the t to the fourth minus 1 cubed. That's nothing in front of that. And then we have that derivative of t cubed plus 1 to the fourth. Well, that's our power rule, right? Power function. So power rule, 4 times t cubed plus 1 cubed. Then, since it is a power function, times the derivative of the base, t cubed plus 1. Now again, if you can do all that in one step, fine. I'll give you just enough rope to hang yourself, because that's what's going to happen. You're going to end up trying to do too many things at once instead of breaking it down step by step. So then I move to the second piece. There's the t cubed plus 1 to the fourth. That hasn't changed. Then we have to differentiate t to the fourth minus 1 cubed. Again, that's a power rule. So 3 times t to the fourth minus 1 squared times the derivative of the base. Right? See, there's a pattern. It is a pattern that exists with these different types of functions. You just have to recognize what type of function you're working with and follow the pattern. So then I'm going to go back in and do the derivatives that I still have remaining. So notice I'm not bothering to rewrite anything until I first finish all the differentiation. Then we'll worry about what can be rewritten. So I've just brought down the t to the fourth minus 1 cubed. I brought down the 4t cubed plus 1 cubed. And then we differentiate t cubed plus 1. That's the next thing that we run into. The derivative of t cubed is 3t squared. The derivative of 1 is 0. So then the second half of it, there's the t cubed plus 1 to the fourth. I just brought that down. Times the 3t to the fourth minus 1 squared. Just brought that down. And then we have to differentiate t to the fourth minus 1. The derivative of t to the fourth is 4t cubed. And again, the derivative of 1 is 0. And now we're done with all of the differentiation. I don't see any more ddt's anywhere in there. So now it's going to be all about first cleaning it up and then rewriting and seeing what we can do with that. So I want to show you something with this one. First of all, I'm just cleaning things up in this first part in that front half, that first big term. I've got 3 times 4 is 12, and I went ahead and brought the t squared to the front. And then we've got factors of t to the fourth minus 1 cubed and t cubed plus 1 cubed to get that. On the back end, similarly, all right, I've got 3 times 4, I've got 12. I went ahead and brought the t cubed to the front, and then I've got t cubed plus 1 to the fourth. I've got t to the fourth minus 1 squared. And that at least cleans up the two terms. Now, we're not going to stop there, though. Now, if you get it to this point, I mean, I'm happy you have the right derivative, you cleaned it up, but I want to show you what could be done next, because we're going to see this happen. Right. So I've got 2 big terms here. Right, remember, terms are separated by addition. I've got this big term right there. I've got this big term right here, each of which is the product of multiple factors. So what I did in the next step was I identified common factors between those 2 terms, and I factored out the common factors. That's all this next step is. You do that all the time when you factor expressions, when you factor polynomials, and you factor out common factors all the time. The only difference is here the common factors, some of them are binomials. They're not just monomial terms. But that's all this next step is. What are common factors? Well, they both have a 12, so I pulled the 12 out. They both have a t. So let me do this. I pulled out the 12. That was a common factor. They both have a factor of t. The first one has a factor of t squared. The second one has a factor of t cubed. What do they have in common? They have t squared in common. So I can pull out t squared. what does that leave me with here? It leaves me with just a t, right? Because that's t cubed. If I pull out t squared, I'm left with t. We do the same thing with the other common factors. Notice I've got a t to the fourth minus 1 cubed. I've got a t to the fourth minus 1 squared. So I can pull out a common factor of t to the fourth minus 1 squared, right? You always pull out the lower exponent. But that still leaves me with a t to the fourth minus 1 right there. Right? I pulled off 2 of them, I still have 1 left. We've also got a t cubed plus 1 cubed and a t cubed plus 1 to the fourth. So again, I can pull out a t cubed plus 1, but I can only pull out t cubed plus 1 cubed, which still leaves me with a t cubed plus 1 there. So I pulled out the common factors. You know, and what do you do when you factor out common factors? You then multiply that by whatever's left. So what's left in the first term? T to the fourth minus 1, right? Everything else, notice, got marked out, got factored out. Plus, what's left in the second term? Well, we still had a t right there. And we still have a t cubed plus 1. But all that is basic factoring out of common factors. It's just a little more interesting because the common factors are binomials in this case. So now what do I have? I've got 12t cubed, back up here, 12t squared, excuse me, times t to the fourth minus 1 squared times t cubed plus 1 cubed. And then all I'm doing from here is just rewriting that last factor in the brackets. So I've got t to the fourth minus 1 plus, I've distributed the t, I've got t to the fourth plus t, and then I can combine the two t to the fourth. And this ends up being my final result, my final derivative in a completely factored form. Right? Because notice, once we finished up the derivative initially, let's see, where do I want to go back to? Here. Right. Whoa, that was not a good idea. And we'll just leave it that way for a second. But once you go, that's where we originally finished off the derivative before we started doing all the factoring out of common factors. And I tell you, it's okay. I mean, if you left it like that, I wouldn't dock you for that, not putting it in factored form. But what we did from there was we actually took that and put it in a completely factored form, right? And so when you see something like this, like when you're checking your solutions, that's what they're going to do in the solutions manual. And so that's what they're doing. They're taking it and putting it into this factored form. Okay? Yeah, so I mean, now it looks ugly. It's not that bad. But it's, again, I keep coming back to the same theme with a lot of this. You've got to be organized and you've got to be neat. Right? You've got to keep track of all the pieces and parts of your function. All right, number 7. All right, so that one was ugly. The next few are going to go a little bit more quickly. Number 7, I've got the function y equals 4 times the secant of 5x. All right, so again, my main thing is I want you to recognize these combinations of functions, these compositions, and then how do we differentiate using that chain rule with these different types of functions. So first, recognize I've got a trig function, obviously, with an argument. So my outer function is the trig function, the secant function, whose inner function is 5x. Now the 4 in front of that, that's just a constant multiple, right? I don't really care about that. The constant times the function, its derivative is the constant times the derivative of the function, right? That's our constant multiple rule. So that doesn't change. But here's the derivative of the outer function. The derivative of secant is secant times tangent. So the derivative of 4 times the secant of whatever would be 4 times the secant times the tangent of that whatever, 5x in this case. So again, notice I didn't change the argument. Then chain rule says multiply by the argument. Okay? So then times the derivative of 5x, which is 5. So I've got 4 secant 5x tangent 5x times 5, or 20 times the secant of 5x times tangent of 5x. Okay? So that's, again, a basic trig function. I differentiate the trig function with respect to its argument, leave it alone. Then you differentiate the argument. Number 8, another trig function, but notice in this case, the trig function is actually the inner function here. Because y equals cosine squared of x, right? That exponent of 2, that's your outer function. You can write it this way, and it's probably clearer and easier to see it written that way, but you need to recognize it in either form. The outermost function there is a power function. That's the cosine function raised to the second power. So I have to differentiate this first as a power function. That's the outermost function. I follow the power rule, which says what? Which says multiply by the exponent. So I've got 2 times the cosine of x to the first power times the derivative of the base. Remember, power function. Use our power rule times the derivative of the base. And so then I've got y prime equals 2 cosine of x times the derivative of cosine, which is the negative or opposite of sine. And then I just rearranged. I brought the negative up to the front. I've got y prime equals negative 2 times cosine x times sine x. And that's a perfectly good derivative. I mentioned underneath that to recognize that that is the double angle identity for sine. I don't expect y'all to recognize those as readily as you do some of your other trig identities. But the sine of 2x is equal to 2 times the sine of x times the cosine of x. And I mentioned this because, again, when you're checking these in your solutions manual, sometimes they will rewrite this. They're not just going to leave it as negative 2 cosine x times sine x. They'll write it in terms of that double angle identity, right? Which, again, I don't care if you do that or not. But I want you to recognize what they're doing so when you see it, you understand what happened, okay? So yeah, they're notorious for that. And if you've been using the solutions manual so far, you already know that they're very notorious about skipping steps. They expect you to understand some of the basics, and they don't write every little nitpicking step down. And then they also do things like this with trig identities. Okay, but I don't expect you to remember those double angle identities, but you will as we see them pop up more often. Number 9. Here I've got f of theta equals the sine squared of 3 theta. All right. So similar to that previous one where I have cosine squared, but also notice I also now have a function in the argument. So there's actually 3 functions in play here. The outermost function is still that power function, it's still the square, whose base is the sine function, whose argument is 3 theta. So there's an outer power function with an inner trig function which has an inner argument, right, inside the trig function. So here's a case of chain rule where we have to employ it with 3 functions. So again, one step at a time. What do we do with a power function? That's my outermost function. We multiply by the exponent, decrease the exponent by 1. And then we differentiate the base. And this is why I say again, if you take it one step at a time, don't try to do too much at once. It's a power function. Use your power rule times the derivative of the base. Then you worry about differentiating the base, right? I don't care about this anymore. I'm done with that. I just bring it down. All I care about is the part that I now have to differentiate, which is the sine of 3 theta. So then my question is, how do you differentiate sine of 3 theta? Well, it's a trig function. So again, I just brought that down. The derivative of sine is cosine with respect to its argument times the derivative of the argument, right? That's our chain rule with a trig function. We differentiate the trig function times the derivative of its argument. And the derivative of 3 theta with respect to theta is just 3. Right? The derivative of x of 3x with respect to x. The derivative of theta with respect to theta. So I end up then with 2 sine 3 theta times cosine of 3 theta times 3. And again, I just rearranged that. I've multiplied the 3 times 2. I've got f prime of theta equals 6 times sine of 3 theta cosine of 3 theta. But there's a case where you actually got 3 functions. An outer function that's a power function whose base is a trig function, which has an argument. That also needs to be differentiated. And so I tell you at the beginning, there's no limit to this. There can be any number of functions. I think typically, though, we're not going to see more than like 3 wrapped up together. But you got to recognize it. Here's number 10. And I like this one just because it looks weird because, you know, I've got a combination of trig functions where the outer function is that sine function whose inner function also happens to be a trig function. You know, I mean, there's no limit. There's no, you know, rule that governs what function can be composed with what function. All right. I mean, I can have a power function within a power function, a trig function within a trig function like we do here. There's no limit to any of this stuff. Right. So you kind of, visually, you can't let it confuse you either. This is not the product of sine times cotangent. That would look like this. If I had sine of a sine function times a cotangent function, it would be sine of theta times cotangent of theta. Right? That's the product of 2 functions. That's not what we have here. We've got the sine of the cotangent of theta. That's why I keep saying you've got to know the notation. You've got to understand the notation. And we harp on this in trig. You know, you have to look at what's the argument of your trig function. You never write a trig function without an argument. All right, so with all that said then, so this is a composition of functions where the outer function is that sine function whose inner function is the cotangent function. So how do we differentiate the trig function? It's the derivative of the function, so y prime is the derivative of the outer function sine, which is cosine, with respect to its argument. So the argument doesn't change, but then we multiply by the argument. So then, again, this part just comes down. I'm done with that. Cosine of cotan theta times the derivative of cotangent. We don't see cotangent a lot, but, you know, it is a trig function. We need to know its derivative. And the derivative of cotangent is negative cosecant squared, in this case, theta. And then again, I just cleaned it up by bringing that negative out to the front. So I've got y prime equal to the negative or opposite of cosine of the cotangent of theta times cosecant squared theta. So that gives you a bunch of examples with some different types of functions. Now, again, like I said, there's no magic pill. That's not the only possible combinations of functions, obviously. But at least it should hopefully give you an idea of what you're looking for. All right, last part of this section. Exponential functions, base A. Right, and by definition, A is a positive. I mean, that was part of our basic definition of exponential functions. The base is always a positive constant. But we had talked about differentiating exponential functions earlier, and we had come up with a formula. We went through this in an earlier section. I think it was actually back in section 3.1, where we said that if f of x equals a to the x is our basic exponential function, we found that the derivative f prime was the function times its derivative at 0. And we say, well, that's kind of a problem, because how can I differentiate the function if I don't know how to find the derivative, kind of thing. You know, we said you can't use the word in the definition, so how can I find the derivative if I can't find the derivative? But what we were able to do at that point was we did make the recognition that for the exponential function base e, that f prime of 0 was 1. And that's led us to that derivative of e to the x being equal to e to the x, because it was the function e to the x times its derivative at 0, which for the base e function is 1. But now, well, what if my base is not e? I mean, what about all the other possible bases for exponential functions, right? It could be anything. It could be any positive real number. Now, ultimately with this, all I care about is that you know how to find it. I'm going to show you why it is what it is, you know, where the definition of process comes from. But ultimately, ultimately, all I care about is that you're able to find the derivative of the exponential function. So here's a recall, always our dangerous statement, going back to some basic understanding of exponential and log functions. If I take an exponential function base e whose exponent is log base e of a, so that's e raised to the log base e, or natural log of a, that is going to simplify down to just a. I mean, remember, exponential functions and log functions are inverses. So if I plug a log function of base e into the exponential function base e, they undo each other, and that would simplify to give me just a. So if those two are equivalent to each other, then I'm just going to take each one of those and raise them to the x power. So in other words, a to the x then would be equal to e to the ln of a raised to the x. Right, so I just raised both sides to the x power. Now remember, this is ultimately the one I'm interested in differentiating, so we're gonna come back to that. Now, rule of exponents. I've got e raised to the ln of a power raised to the x power. When you raise a power to a power, you can simplify or rewrite that by multiplying the exponents, right? So equivalently, that would be e raised to the ln of a times x power. Now again, that's still equal to a to the x. I'm just rewriting. Now, the chain rule. If I'm going to differentiate then a to the x, I could then differentiate this because they're equal to each other. Well, we know how to differentiate e to a power. It is equal to e to the power times the derivative of that exponent, right? That's our chain rule that we just talked about. So the derivative of e to the ln of a times x is equal to e raised to the ln of a times x is equal to the function times the derivative of the exponent. Now the exponent in this case is natural log of a times x. Now remember, natural log of a, that's just a number, that's a constant. A is just a constant, it's a positive value, it's a positive constant. So just like, 2 or 5 or 10, so if I was differentiating 2x or 5x or 10x, what's the derivative? It's just the constant. So the derivative of a constant times x is the constant. So the derivative of ln of a times x is ln of a. So here's the e to the ln of a times x, which we already had, and then times the derivative of ln of a times x, which is ln of a. Now, what is e raised to the ln of a times x? Remember, that is nothing more than a to the x, right? These were equal to each other, this and this. So I can replace that with a to the x. So what do I end up with? I end up with the derivative of a to the x being equal to a to the x times the natural log of a. So whereas before we had the derivative of a to the x being a to the x times f prime at 0, it also turns out that the derivative of the function at 0 is equivalent to the natural log of the base. Whoop-de-doo, I guess. Right? Us math folks would find that absolutely amazing. But for our purposes, all you need to know is that the derivative of a to the x, exponential function base a, is equal to the function times the natural log of its base. I mean, and that still holds true for e to the x. I mean, that doesn't change what we already had for e to the x, because the derivative of e to the x would be e to the x times the natural log of its base, which is ln of e. Now, the ln of e is 1, right? Log base e of e is 1. So I get e to the x times 1, or just e to the x. Right? So it's the same as before. The derivative of e to the x is still e to the x. I don't need the ln of e tacked on to that because ln of e equals 1. But that's the bottom line. So now we know how to differentiate exponential functions base a. So for example, if I have a function f of x equals 3 to the x, what is its derivative? F prime of x. It's the function times the natural log of its base. And that's it. So it's 3 to the x times natural log of 3. Now we could also throw in some chain rule because, since this is an exponential function, maybe I have an exponent that is itself a function, right? So number 2, I've got y equals 5 raised to the x squared. So again, outer function is an exponential function, base of 5. But how do we differentiate an exponential function? It's the function times the natural log of its base. And now with chain rule, times the derivative of the exponent is also in play. So y prime, the outer function is 5 to the whatever, is 5 to the whatever times natural log of 5. And then chain rule says times the derivative of that exponent, times the whatever, derivative of the whatever. So I end up with y prime equal to 5 raised to the x squared times natural log of 5 times the derivative of that exponent, which is 2x. And again, you could do any kind of rearranging of factors or any of that right there. Don't multiply that 5 times 2 to get 10. Those are two different values. That's not 5, that's ln of 5. And that's also 5 raised to the x squared. Those are separate factors. And then times the 2x. But yeah, there's your exponential function. So again, chain rule, you've got to practice it. You've just got to look at all the different combinations and types of functions, and you have to recognize you can't let it visually overwhelm you, and just take it one step at a time. But I caution you, this is the process that usually gives the most difficulty. That is it for that section.